The goal of our graduation project is to enable amputee people to easily interact with their environment by using a 3D printed prosthetic arm driven by EEG signal via AI technology. So, as a consequence, we propose to build an effective, low-cost, and relatively lightweight prosthetic arm that can support amputee patients to execute different tasks in real time without human intervention that will reduce the burden on their family members and caregivers. For innovation aspect, we managed to convert acquired EEG signal into 2D scalogram images by using a sophisticated signal processing techniques and then feed it to a pre-trained neural network to get high accuracy and result. On the other hand, our mechanical design is similar to the humanoid arm as it consists of two links and an effector as much closer to the ergonomics of the natural arm. Also, it can perform several tasks such as hand reaching, grasping items, making extension and flexion for each finger independently. According to our current progress, we'll talk about the following items. In this section, we will talk in brief about different stages of pre-processing phase, started from dataset passing through number of electrodes and the reason behind selecting only 6 electrodes, then complete our discussion about filter, normalization, common spatial pattern or CSP, and finally, continuous wavelet transformation, which play an important role in converting EEG control signal into scalogram images can be fed to pre-trained neural network. The 6 electrodes are selected based on correlation of movement for grasp and lift tasks, so the 3 channels C3, CZ and C4 are associated with motor movement, while B3, BZ and B4 related to cognitive processing in the brain. We filtered EEG signals through using bandpass filter with cutoff frequencies 7 and 30 Hz, which enable us to extract mu and beta band and eliminate artifacts related to eye blink, heartbeat, or muscle movement. After that, the filter EEG data are normalized by subtracting the mean and dividing by standard deviation of the signal. Here we apply common spatial pattern filter, which depend on a matrix decomposition method, so we can extract special features of different classes and also we maximize the power difference between them. This is achieved by maximizing the variance in one class while minimizing the variance of the other class, taking into consideration that all 6 events in dataset are equal in length. The following graphs demonstrate the effect after and before using CSP filter on EEG signal for C and B electrodes. Okay, in this step, we use continuous wavelet transformation, CWT, to transform one-dimension EEG control signal array into two-dimension matrix in frequency domain known as scalogram. We use analytic Morse wavelet as a mother wavelet with a sliding window 400 samples equivalent to 0.8 second duration with 100 sample overlapped. Each of 6 electrodes will produce a scalogram in grayscale format and then concatenate each of C3, CZ and C4 electrodes of the same class to form RGB image of size 224 times 224 times 3. With the same way, we produce another RGB images from P3, PZ, P4 electrodes. So, in total, we have more than 5,300 scalogram images generated for each single class of dataset.
As we converted our signal into 2D scalogram images, we have had to use a deep learning model to extract the features out of the images with high performance, since the machine learning traditional ways will not work out with this form of data. The training of the deep learning models requires a huge amount of data. Also, it needs expensive GPU processors and consuming a lot of time. We chose to use pre-trained network. The time by using pre-trained weights, adding a new fully connected layer to fit our model. And after trying many pre-trained networks and according to the accuracies we have got, we selected ResNet 50. And here is the architecture of this network. Since the dimensions of scalogram images of the wavelet transformation is 69 times 400, we have had to resize it to the input shape of the ResNet 50, which is 224 times 224, and we have done the resizing using the bicubic interpolation method. After the pre-processing of the data and the resizing of the images we have got from the scalogram, and after the hyperparameter tuning we have done, we decided to split the data into train and validation by percentages 80 to 20 respectively, and using Adam Optimizer, which gave us the highest accuracy among the optimizers we have tried. Also 10 epochs were good enough to train the last fully connected layer we have added.
In this section, we will talk about the mechatronic system. At the beginning, we studied the anatomy of human arm to know more about its nature and trying to mimic the arm for reaching design that meet the requirement of amputees. We found that human arm consists of two links and end effectors. So we calculated the kinematics of arm through using the Lagrangian equation, which helped us to know the torque on every joint tau1 and tau2 as shown as in the following figures. According to our mechanical design, our prototype is pretty similar to human arm, as it consists of three main stages as shown as in the following figures. We took in our consideration the concept of ergonomics in design as much as we could to be more comfortable for amputees. Our prototype can perform several tasks such as hand reaching, grasping items, making extensions and flexion for each finger independently. For interfacing servomotor with ESP32, we managed to implement the first stage in our mechatronic system through interfacing the output of pre-trained neural network with ESP32. We used servomotor with torque 0.45 Newton meter for every single finger to mimic the human nature in grasping items. In this section, we will talk about the technology used in our project. The first phase is flying dataset sim real time, as it depends on recorded dataset, making signal processing and algorithm translation on laptop. After that, sending commands to ESP32 microcontroller to control mechanical design. Second phase is using online dataset real-time as we acquired EEG signal from NeuroSky headset and then sending them to SDK NVIDIA Jetson Nano to make signal processing and algorithm translation. After that, ESP32 microcontroller receives the commands from NVIDIA and control servo to manipulate the movement of our prosthetic arm. For applicability, we managed to apply our signal processing technique in the first phase successfully, and we will move forward to the second stage, which is real-time signal processing. On the other hand, our prosthetic arm design has a relative lightweight and also low in cost due to the technology of 3D printing and manufacturing. Also, we use a powerful microcontroller with low cost. So, as a conclusion, we can say our proposed method can be implemented in real ground.
According to the World Health Organization report in 2021, there are 30 million people need prosthetics all over the world, and probably most of them lost their jobs. So our aim is to design a prosthetic limb with relatively low cost that most of people can afford to improve mobility and the ability to manage daily activities, as well as provide the means to stay independent.